Hello, and welcome to the Sinumerik online webinar series. Today, we'll be talking about ShopTurn setup and programming specific to turn mill B-axis lathes. I'll be Pollock. I'm the head of the Virtual Technical Applications Center and a source available for you if you have any questions specific to operation and programming topics. Let's highlight some of the things that we have coming up. In April, we're going to be doing a part programming webinar specific to a shop mill in mode, so in-process measuring. After that, we have some additional webinar contents that will be put out shortly. Now, all webinars can be found to our main CNC for You website. So if you want to get back to some of the previous webinars posted, you can use the direct link, the CNC webinars link, or you can use our main website and go over to the webinars section. Additionally, you want to check out the CNC for You website for a lot of other material. There are kinds of video tutorials. You'll find documentation and manuals there. It's a great resource for anything Sinumerik based. You can check out our CNC training offering. We offer in-person workshops or training classes at our Technical Applications Center in Elk Grove Village, Illinois, that's right by the O'Hare Airport. All classes are free of charge. You can come in and attend the classes. We have 3 different levels of operation and programming, going all the way up to an advanced 5-axis level 3 class as a service and maintenance class. So take a look at the link. You can download the agenda and you can register right on the forum for these upcoming classes. Today's content is going to be specific to our Siemens Sinumerik 840 DSL control. There are functions in this content that is only really accessible or available once into the 840D. A lot of topics we've done in the past transcend working both the 28 and the 840. Here, this is specific. We're getting to a level of advanced functionality that's specific to the 840D control. We're going to be talking, as I mentioned, about B-axis technology lathes, or turn mill technology lathes. So we're going to look at the kinematics, get your head around what do we mean by a B-axis, what do we mean by a turn mill tool. We're going to get into how do we hand machine in an operation, a setup and operation scenario, setting tools, calibrating tools, that kind of stuff. And look at a live programming example and go through all of the typical operations you would do when programming a machine with this kind of technology. We're going to start with some basic features and functions. Everything's going to be around the ShopTurn built-in conversational programming environment. Find a lot of these features and functions will mimic or mirror the functionality we would be doing if we were writing a G-code program. I would to reference before we begin where you find some supporting documentation on the topics we talk about in this webinar series. So this content of this topic, you want to look for the ShopTurn Operation and Programming Manual. You can find at our supportindustries.siemens.com website, or portal we like to call it. And there, generally, either you search for the content name. In the case if you search for ShopTurn Operation and Programming, you're going to find a ton of manuals or documentation there. So what I suggest is just write down or jot down the document number right there on the right side of your screen, the 6SC5398 number, and do this for that. That's going to drill you specifically to the ShopTurn manual. If you just look for ShopTurn, just pay attention to the date of the manual. The manual we're referencing here is the 2008 edition. But you're going to find a working with a B-axis chapter, and that's going to really sort of back up a lot of the topics we talk about today. Not everything, but certainly, especially from the setup side and the operation side. Take a look at those features or those chapters, those sections. Additionally, this is a webinar kind of building on previous content, so building on some of the more entry-level ShopTurn webinars. But from an advanced perspective, this is specifically the next series up from a webinar we did on programming sub-spindle lathes. So in that webinar, I would certainly recommend going back to it, take a look at it. You can find it right there under the CNC webinars website. If you click on the turn, it's going to be the first one you see pop up. And then you can view the recording or download it for viewing later. There's a lot of material that we're going to talk about here that I'm going to jump over because we've talked about it in detail in the previous webinar. And there's a lot of stuff for us to get through, so I don't want to obviously spend time reiterating stuff we've already talked about. So again, if you haven't seen it, I would suggest going back and taking a look at that webinar. Okay, so the thing we want to talk about, and it's really kind of a little bit of a stigma right now in the industry, is what we call this technology. Is it a turn mill? Is it a mill turn? Confusion with this terminology. So originally, when this mixed technology style machine came about, there really was only one configuration type that was leveraging and milling, and that's really a lathe that we're incorporating this milling functionality. And in the last few years, that motor technology has gotten to a point, specifically leveraging torque motors, where you can take a player of a large 5-axis milling machine, get it to run at RPMs where you could actually turn at. So proficient in both sides of the technology, we started changing the terminology a little bit. So instead of calling everything a mill turn, we're specifically calling it the base technology of the machine tool built on. So it was originally a lathe type of framework that milling has been added onto, and the base control, or the primary technology of the control, is a lathe that has had milling turned on, then referred to as a turn mill. In addition, if it was a milling machine frame that's turning capabilities, and from the control's perspective, the primary technology is milling, and it has turning functionality added into it, then it's referred to as a mill turn. Okay. I mean, you certainly refer to them as either or. It gets a little confusing. You're not always really sure what the base technology is. So that's what we've adopted. We call turn mill or mill turn. So today, yes, we're specifically talking about a turn mill. It's a lathe with milling functionality added onto it. See, when I find it in front of the machine, what's going to be different than what I've seen in past configurations of the Sinumerik control? Well, really, the biggest thing is the B-axis functionality, right? So that the number of spindles that would mirror machine has a main spindle, sub-spindle, and live tooling turret. See the same number of spindles, but here now we have a B-axis. From the physical configuration side, I have a machine that has one primary driven spindle, just like a machining center spindle, and can program it through the axis orientation in any range of motion, generally about at least 180 degrees of motion, sometimes even more, 120, 130, so I can start to swing it around. Now, how did it configure differently than a standard traditional lathe with a normal traditional style turret? This is where the reference kind of comes from. So the main is all going to be referenced from the spindle. This is a pretty common commissioning method when you get to this advanced technology. So it's a main sub-spindle machine with a more traditional turret on it, or a B-axis lathe, everything off the primary spindle face. Instead, a turret is going to work all of its offsets based off of the datum on the turret face, somewhere relative to the turret body. And offsets are going to stack off that. In a B-axis lathe, that datum is actually the center of the rotary, and a offset working in the background of the control that's managing what we call our kinematics. That's the makeup of the machine. And then what will happen is there's a known value that goes from the center of the rotary to the gauge line, which is generally the face of the spindle. Your offsets are going to stack from there. So when you set up a tool, the offset is going to be from the spindle face out. The system is actually managing value from the center of the rotary out. And that's how we can dynamically adjust as we start to rotate the B-axis around. So what am I going to see in a little more detail? This would be a very typical configuration of machine tool in this analogy. So we have XYZ milling spindle around in space, a main spindle, any number of different terminology. Each builder likes to kind of change what they call spindles. Usually the first thing I do when I get in front of a new machine is just figure out what's the terminology that they're using. Is it S1? Is it C1? Is it some other number? Some just like to always use the same terminology of spindle locations, and then if your machine just doesn't have that type of spindle, like a secondary turret, let's say, then they just skip over that one. So that's a pretty common method too. When looking at the B-axis, it's important to start to kind of head around where is this B0, where does everything drive from. So if you look at the image on the right side, this is a very, very typical configuration of setup for a B-axis lathe. The primary B0 location is at 9 o'clock, so the position that you see that head sitting in, which is the primary tool position facing the main spindle. And that's going to drive relative to that offset. So if I want to tell the tool to swing down from 9 o'clock to 6 o'clock, I'm actually going to give it a B90 positive value. And she's going to rotate counterclockwise down to that position. If I want to get to the sub-spindle, I get 180. So the thing to kind of get around is where is it referencing the B0. Different builders can do different things, but this would be probably one of your more common methods of setting up these machine tools. Now, I start to drive this B-axis around through the interface screen. What we've done was we've incorporated two additional fields that you're going to see in above our standard cycles and functions. So first, in the TSM screen, we shall be used to the TSM screen for allowing us to do tool changes, fire up our spindle, do stuff like that. Well, you can now see a what we call beta field, which is that little B insignia, and our Y field, or our gamma field. So beta is going to refer to the angle that we're driving the B-axis to. And gamma is going to refer to the spindle orientation of the live spindle for that milling spindle. Imagine, or if we reference the right side image, I have a turning tool and I want to start to orient that and then move it around in space. Certainly I can swing the B-axis with the beta field, 0 again, which is at 9 o'clock, swing it down, and use the gamma, which is the orientation of the spindle, to flip that sort of around. My little right-hand view there, that right-hand turning tool, if I want to cut the outside of the part, I leave it at some angle, probably 45 degrees or less, could be 0. And my orientation of my gamma, or my spindle, that's 0. But if I want to take that same tool and now come down the face of the part, I may want to invert it at an angle greater than 45, probably all the way to 90. Out past that point, my insert's pointing the other direction. This is a right-handed tool. So spin my gamma or my spindle around 180 degrees just by inputting a value of 180. And the system now allows me to put the tool in such a fashion where I can come down. Nice about the system is it's going to track appropriately, handle the spindle directions based on the orientation, and also dynamically adjust for your offsets based on this orientation. But you have to use the beta and the gamma fields to drive this. So let me show you what I'm talking a little bit here. I'm going to transition over to Sinumerik. Sinumerik is our machine tool control emulator. Obviously, I'm running this one on a PC, but the process would be the same. Say, for argument's sake, I have a tool. It's sitting at the B0 or beta 0 location. I got a standard tool in the spindle, and I want to see kind of what's going to happen. So I'm going to position this machine to a location. So to 300 millimeters. This one has to be metric. Obviously, it'd be the same if we were running this thing in inch. And put the machine to this location. And I can't quite get there. Oh, let's load up a work offset real fast. And offset's turned on. Okay. Let's go to that position again. 300 Z0, and if you can picture it in your head, the handed tool is pointing at 9 o'clock or at 0. Now, what happens to the numbers if you use the TSM field, type in a base value of 40 degrees? So I'm swinging it down to basically that 7:30 position, right? So I'm going to cycle start. The machine drives down to 45 degrees. But physical position and location changed. Now, the machine didn't move the linear axes. This is a dynamic offset, but that's not a 5-axis toolpath per se. But what it did do is it calculated, based on that move, you have to go to get back to that 0 point. So the system is automatically calculating for that. If I look at the actual motion of the machine, nothing really occurred. So if I'm going to be sitting back here at a 0 and I look at my actual values, right, and I swing the system down, I'm going to swing it down. The actual values is showing what the motors are doing. I swing it to 45. The display doesn't change. But this did recalculate. That's how we kind of track, and we can automatically adapt for however I decide to set this tool. And it's driven by the fact that we have the cycle on currently on this machine. That's what's tracking these numbers. This is our dynamic fixture offsets. What would have happened if I did the exact same move? So I'm going back to 0. Same move, but I positioned it with the B field here. Drive it with a direct axis of B. I can adjust anything. So you see numbers didn't change. It also the same. So you want to be very careful when you start to move these machines around and you're using the functionality that you're driving it through the beta and the gamma field, because that's gonna allow the rapid calculation of the offset. So now I can go back. And I'm going to want to be a safe spot, obviously, before I tell it to move, because it's going to swing that tool down. But that starts to track, allow the system to manage the point in space where you're sitting at. Okay. So this is start to handle working with my live spindle with this gamma field. Build the tools. I'm going to build them. Again, everything is at that 9 o'clock location, or that B0 location. You're going to make a tool just like you've made probably 1,000 times over, building different tool configurations. Now, with the basis lathe, I think that the tool is sitting in that base 0 location. So that's where my cutting edge orientation position is going to come from. So when I go to build that new roughing tool, and I go to look at that first cutting edge option, that tool sitting at a B0 with gamma, or the spindle sitting at 0. If I have a right-handed tool, I'm going to use the first option. That would be used for OD work, but now I have a B axis and I can move things around. I'm not limited to just using that tool for OD work, right? I could use it pointed at the B, or pointed at 9 o'clock, a spindle orientation of 0 for an OD turn. Now I can index my spindle 180 degrees, take that same tool, right into a bore, and do an ID turn. So that's what makes these B-axis machines so much more versatile. I can start moving this cutting edge around anywhere I want in space. I'm going to build the base orientation of the tool, it's left-handed tool, at my, in this primary configuration. Then use the third orientation field over, which would be typically what I would have done for a boring bar. The offsets, everything is going to work off of a gauge line. Typically what you see in these machines is HSK 60 or some HSK mount. So that means that the gauge line is truly coming off of the spindle, because that's where an HSK contacts. If you happen to have a Cat 40 or something, then you do need to just know where gauge line is, because in a Cat 40, gauge line is actually inside the spindle. A big plus, even though they're contacting off the face, the true gauge line is still inside the spindle. But the offsets, our WF and our LF, our length and our length in Z and our offset in X, that's coming from that gauge line. And the system is going to manage that distance that I mentioned earlier, which is the center of the rotary to the line or face of my spindle. That's happening in the background. And that value is critical, because if you imagine that B-axis around, if I know that distance, I never come up with a calculation of where that tool is now that I kicked it down to 45 degrees. Nature. So as you start to do some tool setup, you're going to see the offset values are going to be that distance. You could obviously have set these tool offsets up externally and just plug the numbers directly in. Now when we're turning tools, that's going to be a little bit different, but it's certainly simpler actually, because in this case there is no X offset. It's a rotating tool. Everything's held concentric to the center of the spindle. Give it here is going to be my progenitor distance, that I1 field, this from gauge line out to the tool tip, and cutter diameter. When you build the orientation of the tool, you don't have to worry about all the different handed or orientated tool holders that you would have in a traditional turret. You're going to drive it around the B-axis. So everything's going to be built at that 9 o'clock position. So the tool is pointing towards the headstock. You're going to swing the tool from a facing tool to a peripheral or oriented tool to a back turn tool. That's going to be handled with the beta and the beta field. And you don't actually even have to worry about gamma, right? The tool's spinning. So there's no worrying about orientating the live spindle portion of it. Drills, build all your end mills as if they're pointing toward head socket 0, and then let the system swing them around. When you get to this more advanced technology, of course, you kind of do more things. So there are some new tools that to become available to you in this technology range. And one of the tools that's pretty neat is what we call a multi-tool. Multi-tool allows you to have a single tool location, but it can handle up to multiple types of configurations. So here on the image on the right, you've got a holder, and it's holding 2 different types of turning tools, probably a roughing and a finishing tool, and it's even holding a threading tool. That's a multi-tool. Now, machine's configured for multi-tool capabilities, then you will see the option multi-tool a selection under favorites when I create a new tool. It's pretty simple. All I'm going to do is I'm going to select the multi-tool field. Once I want to create a multi-tool, I'm going to give it a unique multi-tool name and tell it how many locations I want. I'm going to be able to control the orientation of each location. I'm going to put a checkbox in the angle input field. Checkbox out, then it's going to automatically set the spacing between each tool to be a constant amount. With that, then I get a field where I'm going to see the multi-tool in a specific tool location. That's, in this case, I'm in pocket 10. And I can build however number of cutting edges I told it, or however many of locations, shall I say. I told it within that multi-tool. And it's like I'd build any other tool. But what's happened is when I tool change the multi-tool, I have number 1, the CNMG, or number 2, the VNMG. It's going to grab and bring in all of these tools in one shot into the spindle. To build these types of tools, let's kind of transition over and show you a little bit of what's happening. So, as a review, I'm building tools, build it with the orientation sitting in the 9 o'clock position. So a standard right-hand OD tool, I'm going to use this first position. If it was handed tool, I'm going to use the third position over. And my round tools are always going to be built sitting the B0 location, and then you're going to swing them around appropriately. Now, with the multi-tools, here I have a couple pre-built, or I can create one. It's going to go down to a new location, and when I hit new, I'm going to see the multi-tool field. That's also what this MT column means. So a lot of times you might see that your machine has MTLO. You're not sure what it's referring to. It's referring to multi-tool capability. The positionable spindle for this to work, however. Back to multi-tool, say OK. Tell how many locations we're going to want. Give it some kind of unique name. So I'll call my multi-tool number 3. If I want to type in the angles or not, and then build the multi-tool, and you get these 3 different locations. And these are physical locations that are all tied to the same tool. Now, it's going to be the same process. Maybe I'm going to make a left-hand tool. So I'm going to call mine a CNMG. Like my cap to be on. Smart. G, I don't know, 331. Left all mine. And then I build the tool from there. And then you would certainly build up the other locations. When you change it, you pick the tool like you normally would, and it's going to automatically go grab the multi-tool and then orient the spindle to this location number. That's the multi-tool function. You're going to start to see the multi-tools become popular in this type of configuration because certainly it saves tool locations or tool changer locations. 3 tools in one pocket of my tool chain. Okay. So turning back, now that we've kind of talked about the setup and the creation of tools, the next thing would be setting my work offsets. This is going to follow that previous webinar I referenced, the main spindle machine. So here I'm going to set up 2 work coordinates. I'm going to have a primary work coordinate at my main spindle left, and then set up a secondary work offset. In my case, I'm going to use a G55, 54, 55 for sub-spindle. That one is going to be the one that has the mirror function in it. And the mirror is very important because not only is this now going to manage the Z direction like it did in the previous webinar that I showed, but this is also going to handle the beta and the gamma orientation that you're going to start to see when we write a part program. I can still methodize everything as if it's my main spindle, and then when I apply it to the spindle, it calculates the appropriate orientation angle has to drive the B-axis to, what has to do the live tool as far as positioning of my gamma, and then additionally, where offsets are, what direction the Z is moving in. So all that's being handled by a simple mirroring of the Z-axis. So it dramatically reduces the complexity of programming, switching between main spindle and sub-spindle and all that kind of stuff. Now, using this method, it's very important that your machine is set up properly. Set up properly specific to the work holding. We're going to want to make sure that we have the accurate information sitting in this chuck spindle data that's underneath the setting data in my offset table, and that's going to stack all these offsets. And we went through this again in a lot of detail in the previous webinar, so just make sure you kind of reference that. You got to make sure that the chuck body and the projections are all known here, especially when we go to do the handoff, start working on the back, counter spindle, use all these numbers to calculate, and it'll actually write the work coordinate for 50 for you. You don't even have to touch it off, but you do need to have some valid numbers here for this all to work properly. Now, setting tools, you as well have the beta and the gamma fields, just like we looked at in the TSM screen. So here, make sure you either leave the tool at the orientation it was in after tool change, or if you need to move the tool, you don't move it with the hand wheel, you don't move it with the position screen, you drive it to location using the beta and the gamma fields. I can't stress that enough. A couple arrows, and those are just a quick input. So what will happen is if I have the arrow pointed to the left, that would be just telling the beta to go to that 0 base position. If I have a down arrow pointed, it's going to go to 90 degrees of the B-axis. If I have a right arrow, it's going to go to 180 degrees. So just shortcuts to be this thing around a little bit. Certainly the gamma is going to be the positioning of the spindle. So the 180 are automatically going to propagate there, or if I choose the blank one, just like the blank in the beta, I can type in whatever angular value I need. And then from there, it's just going to touch off like any standard tool would. Down, come to a known diameter, take a light little cut, mic it, plug it in the X0, whatever diameter I'm on, and you've just touched off that tool. And the system, taking into account, obviously, the distance from B rotary center to gauge line, it's plugged in that value, like we looked at earlier, from the gauge line to the tool tip for you. In my Z, I'm using the beta and the gamma fields, and I'll be touching to a workpiece if I'm using the reference point workpiece option, or we also have the ability of touching off to the main spindle or the main chuck or the counter chuck. So in this case, we want to see you come over and bring the tool physically touching the chuck face, not the work holding face. So if you look at, again, those 2 stacked offsets that we're showing you for the chuck body and the clamping, going to touch off to the face of the chuck body. If you choose that, it automatically does the calculations for you. Have presetters, you can just drive up the presetter, and that all gets handled in the back end for you. This would be how I would be doing it if I want to do it manually on the machine. So now we got the machine basically set up. We've driven around a little bit, and we kind of get an idea of what's happening from the operation perspective. Now look at the part programming. We're going to do a simple part programming example. Intentionally, I made this pretty basic from a geometry standpoint. We're going to use some standard turning cycles, facing cycles, but this is all about how are we manipulating the tool with the B-axis. So we're going to come in, we're going to turn an OD boss. That's going to be the boss on the right side view. And then on that right side, or while it's clamped in the main spindle, we'll do some slotting, some drilling, some peripheral drilling, some face mill on the peripheral, flipping back and forth. Then we're going to transfer the part over and do some back operations. So we're kind of going to break it down in steps. So we'll start with a basic OD turn and then transfer our part and then do a back turn on it, just so you can kind of start to see how I can move a turn tool from the main to the sub or counter spindle. And then we're going to go back and we're going to add some primary feature to that first operation section before I transfer the part. Today, we'll have a complete part machined. The goal is to not obviously get you comfortable with how we're handling the B-axis in a facing or a peripheral orientation, but when we get to the later operations, we're going to then create inclined planes, and they're drilling or milling relative to an inclined plane. And this is where the power of the B-axis really starts to become evident. We're going to go in, we're going to create a part program like we normally would. We're going to jump over to our program manager. Once we're there, we're going to use the ShopTurn programming functionality to this part program. If you are a G-code programmer, we'll do this webinar in the future specific to G-code, but a lot of the functionality we're talking about here, if you're doing any cycles out of control on the G-code side, is going to be mimicked or mirrored, let's say. So the swivel cycle in G-code, cycle 800, is the swivel cycle that you're going to see. So there's a lot of good topics here, so you can kind of apply what we're talking about today even to a G-code program, because the functionality and the methodology is really going to be the same. Go in, we're going to start our program, and the first thing we're going to build is our header page. And in the B-axis technology world, there's really nothing new or unique to the B-axis per se when you come to the header page. This is all kind of mimic dealing with a machine that has a main spindle and a sub-spindle. So the drive functionality, the ability of obviously controlling multiple spindles from a max constant surface speed perspective, and then the Z2W field or staging of the sub-spindle or the counter spindle. That's all going to be handled. We're not going to see anything unique to the B-axis until we get in and start to do some physical operations. So first, let's start a program, and then we'll build our header page. So I want to go over to Program Manager, go over to Part Program Field, and let's create a program. Here I have a bunch of ones that we were fooling with before. I'm going to get rid of some of these. We don't need these programs. Done. Right. So I'm just deleting a few, making some space. I'm going to start a new program. I'll turn program. Give following my standard rules: letters, numbers, underscores, nothing else, nothing less. Call line sample 1. Say, and we're in our header page. So, like I just mentioned, there's really nothing unique here. If you're at all comfortable with driving a machine with the sub-spindle, these are the same features and functions. So the scribe for the primary work offset, if I have a known value that part sticking out, again, this would be the total offset from spindle face all the way out to the work offset. I plug it here. Just with this, because this is going to overwrite whatever's sitting in the work offset in a table. So back out here, and I go to my work offset, my G54 has 175. If I put value, if that's truly what I want my work offset to be, it's describe field, it's going to get overwritten. So be careful with that. I don't usually use the describe function for my spindle. That's I'm in an example where I'm doing heavy production. I know from the potential of an operator maybe stepping on an offset, then I can just let it rebuild it each time. If I'm running the machine and I know I'm going to come over and touch front of my part and set my work coordinate accordingly for running the program, I don't want to use describe. So stock, I guess I get a basic 100 millimeter blank. It's 150 millimeter overall. We're going to stick 75 out for the first clamping, and then we'll have a 75 mil for the next clamping, just keeping things pretty simple. Values, I'm just going to have an incremental 5 millimeter retract. Same position for tool change point. So this is a value that I like to get very visual when I'm out on a machine on. I'll pre-position the tool in a safe location. With these B-axis machines, I certainly want to think about the swinging of that B-axis, maybe with the lowest tool potential. I want to try to get as far away. Some of these machines get pretty compact, so you got to be careful starting to swing things around. Here I'm going to use a value based on the machine coordinate system. I'm driving the machine to 550 mil and Z of 750. And really that's just going to be, again, this is a machine coordinate value, so it's based off my spindle face. The machine has 600 millimeters of max travel X, so I'm off that. And this machine, I think, is somewhere around 1,400 millimeters in the Z, so I'm basically centering my Z axis. Once you have work holding stuff on, what is an optimal place? And you jog the machine's location, just use the teach function to teach it in. Safety clearance, certainly my max RPMs, not too worried about it for a webinar virtually, but I would put legitimate numbers here. And then where do I want to stage my sub-spindle when I'm done? So usually I'll send the sub-spindle all the way back or just about back to the extent of the travel. So I have maximum amount of clearance between my two spindles. If production and I'm a larger machine and I don't have to go all the way back, I want to save some time, then you start to truncate everything up. You just want to be careful with clearance because, those heads, they're decent size. So, if you're sitting at a B0 location and you're going to come all the way down to maybe bore a hole, you got to accommodate not only the projected distance of the tool, but that whole head. Just be careful. That's where clearances become a little tight. So our header page is in. Now we're going to get to our first turning operation. So looking at our content, we're going to do a simple OD turn. Not all that complicated. We're going to machine from the 100 millimeter OD down to a 50 millimeter OD. But you're going to see that even in something as simple as a stock removal OD turning cycle, you have the beta and the gamma fields available for you. That's going to let you drive around the orientation, and the system's automatically going to manage it. What happens is this cycle, on the tool change, would plot the orientation angle that I want to rotate it to, then to start point and begin machining. So that wouldn't happen after the tool's already been positioned down. And we're just going to be driving that base orientation of the turning tool. So here, we'll probably do it at a B0 location and machine it, and then we can kind of flip it around so you can see that. So let's add this into our program. Now I'm going to bring up the print just so you can use it for your own reference. And what we're doing, we're machining this area. So get view A on the right side. We're just turning this 100 millimeter stock down to a 50 millimeter OD. Pick stock removal, and I'm going to do my basic stock removal. I want to go to an appropriate tool. So here I'm going to use my right-handed OD tool and come in, and these are the new fields. So how do I want to drive my B-axis? Do I want to just tell it, hey, go to B0? Do I tell it the physical angle? Do I want to swing it all the way down? And then what I want to do for the spindle. And you see when I highlight it, the yellow or the gamma field goes yellow. I can type in a value, or choose the preset 0 or 180. Any one of these, and quite your head around it. Don't worry, try it. Installation's going to catch you if you choose a solution that's not workable. The rest cycle is the same as you guys have always used. Feed speeds, strategy, where am I starting, where am I going, depth per cut, all the normal stuff. Accept it, and now as we start to simulate or run, we're going to see our turning scenario. Now the trick here is pay attention to the screw you see on the insert, because that gives you a reference of where things are positioned. Also, I'm going to slow down my override. Go a little lower. Take a look at the orientation, right? So this is a 55-degree insert with minimal leaf angle, probably 5 or 7 degrees. So you see that that insert was almost vertical against this back wall. So as you start to drive or control the B-axis, maybe I plug in a value of 45, simulate it, it's going to tell you whether or not it can get to that location. So if you choose a value too large for it to go to, so maybe I to 10 or so, it's going to limit or not. And you maybe flip some things up. So you'll control what you want to do based on these values. Now, if I want to totally flip the tool around, right? So I go to 90 and go to 80. That's going to turn the tool upside down and move it around for me. And watch that. I don't, because now I'm flipped over. So you can kind of get an idea, even visually here in simulation, on whether or not you see that little screw detail based on what position that spindle is in. So play with it. If you think that you don't quite have head around the orientation, don't be able to fool around with it. Simulation will catch if you've chosen a solution that's not viable or not possible. Okay. Go back to a base 0 location, and that's just holding the tool sitting at 9 o'clock. And now we're going to go and take a look at a simple transfer. I'm going to turn it, and now we want to do a transfer. So the transfer is going to be this, as you've seen up to now, just including a beta and a gamma field. So this is allowing you the option of telling it you want to swing that B-axis during the transfer method. I said earlier, clearances in these machines. So when I send the machine up to its clearance position, which is to the machine location found here in the cycle, as that be, and if I know I'm going to immediately take that tool and come down and work on the sub-spindle, maybe I want to position it to 80, right? I can have it swung there, let it do the transfer, and now I come straight down and start doing the turning, and the tool's already over there. Or let it handle it in the cycle. Other than that, it's the same exact process. The D55, that's handling everything for me as far as once I get to the counter spindle, so I don't have to worry about that. So this is just going to be driving that initial location during the transfer. To start the transfer is going to be a standard pick and place in this example. So just going to come over, counter spindle, grab my part. Basically my jaws would just be touching, so I probably have a little bit of index offset between the two jaws. Bring her back to that Z2W or safety location that was stipulated in the header page. And then we're going to go in and we're going to start to machine the other side. Important when you start to methodize the counter or the sub-spindle operations, that you remember that you're still always programming everything as if it was in the main spindle. 55, the mirror that's handling everything. So it comes to the beta and the gamma fields, think of it as if you're on the main spindle. The system will automatically orient the B-axis, orient the spindle, and handle the Z direction. So it also handle the direction of the spindle of the sub-spindle, because that may have to spin backwards. It calculates all for you. You don't have to think anything about that. Just always sure that you're driving all the data as if you were sitting on that main spindle. So that operation in, those operations in this case. When I get to the various fields, I want to go to my counter spindle option. If I want to control the positions, I can plug the values in. The rest of this is going to be the same as I normally would for a pick and place. Where do I want to send the machine as a safety location? Where am I sending the live tool in this case, so the milling spindle? Fluent, what directions are my two spindles running in? What RPM are onto the part am I going? What's the reduced feed? What reduced feed rate? If I want to travel to a fixed stop, do I want to apply pressure? Am I drawing the part out? Cycle. Again, we're just doing a pick and place. What's the work coordinate that I'm going to use once I get to the sub-spindle? Very, very important. Am I describing the secondary work offset? And here, I like to use the describe method. You have to. You could stage it. But the system, as long as I set up my chucks properly, does calculations for me. So I don't have to think about that. And referencing that previous webinar, go back and check it out if you haven't seen it, because I talk about this in a lot of detail. And we really start to show you how those numbers get calculated. It's pretty cool. So what's the overall blank? It knows how much it's going to be stick out by how much I throw it on. So stick 75 mil. And we want to send the sub-spindle when I'm done. And you don't have to go back to where the header page says. This is what's controlling where I'm going to go to after the transfer. Or do a simple turn, but I'm going to the left side of the feature, and I do have a chamfer here. So I still use the stop removal cycle, but I'm going to use the one with chamfers. And I'm using a B0 and a gamma 0 orientation. Typically, right, I'm machining from 100 down to 50, 50 mil back. I'm using a chamfer of 10 mil in this back corner. And depth of cut, normal stuff. To work properly, this actually has to jump over and automatically orient that spindle for me, and that B-axis orientation to 180, and that will automatically be handled. So turn, I see insert screw, so where I'm sitting as far as the B0 and the spindle orientation, there's our transfer. And see the insert screw anymore. And the spindle, the counter spindle, is actually running in reverse. System will do that for you. By using the mirrored work offset and allowing us to track the beta and the gamma. If you want to do all this with B-axis positions and positioning the spindle, you can start to see how complicated this becomes. What direction do I have to run the spindle in? Am I inverted? Am I not? It's just tracking all that for us. So start to get to some little more intricate or interesting type of features. Let's do some milling. So come to the milling cycle, you're going to notice there is no beta and no gamma. Because based on the orientation of the geometry, I tell it, is my face, is it on my peripheral surface? That's how we're going to know how to stage the B-axis. And I need to know the gamma because the tool's spinning, right? So that one's easy. So the configurations I've used before, you may or may not have seen the phase Y function. Phase B is something new. We're going to keep for a little later in this session because that's what's going to allow me to handle my inclined planes. So just as simple as picking either a phase C or phase Y strategy. Phase C would give you C-axis motion for milling this slotting tool path. Phase Y would hold the main spindle stationary, or whichever spindle I'm running, shall I say, stationary, and use the Y-axis of the machine to between X and Y, machining this tool path. And then I need to go into the peripheral, or that's the part. I'm either going to use the peripheral C or the sheath Y, and we're going to see that in the next operation. Here we're just doing a standard slotting cycle, open slotting cycle. I'm going to add that to my first op, because if we look at our part print, see that the slot is actually on the right side. What I'm going to do as well, to keep from doing the transfer, because we're going to add a few operations to this main side, and let the other stuff get pushed down. I'm just going to put a quick little G-code line in of a stop. This way, I don't have to worry about simulating the entire process the whole time. We can kind of work on the part, get done, and go over to finish off the back section of it. And open slot. The tool, I'm going to that's pointing towards my 0, but always going to point at. Because again, the axis is going to handle swinging that tool down. So all mills in my end mills should always be built, unless some kind of right angle head in there, should be built towards the B0 location, or that 9 o'clock position. There again, there is no beta or gamma here, because everything is being driven based on what I choose. All right, am I working on the outside surface? I'm on face, and we'll do its calculations from. The rest is just going to be standard. You know, where's the center? What's my technology or my tool path strategy? Conventional mill, one slot, multiple. Now, the orientation position, that becomes important. How I can kind of clock where the slot is. So have this slot be at C0, basically. So it's going to machine a slot straight up and down. And then think about that later, my other features, right? I got a couple flats I got to put on this part, and some drill holes, and they're 90 degrees off the slot. So you just got to pay attention to that. But that's how I can kind of clock the feature around. This is just your center, right? Center of it, top of the part, length and width of my slot. So 16 mil wide, 50 mil long, something just a little greater than. And orientation if I need to. Depth. This radial engagement, my barrel step over, I'm doing a 30% cutter diameter engagement. Depth pass. So again, this one just take all one cut. Do a material for a finished cut. Simulate it. We're now going to see the first turn feature, and we're going to see the machine slot come into play. Now I'm going to look at 3D here, give a little bit of rotation. A face-wise strategy, so you're not going to see the spill oriented to the C axis. If I use the face C, then the axis would be held stationary. And we get our slot. And the B0 position knows based on the location of the slot. And because I got my program stop, if I go start again, it would have continued on, done the transfer, and moved on through the program. For us, the next feature is actually be to face off these two flats. So not only do I have the flats created, but I can drill or maybe tap or whatever I'm doing some on these flats. Before, no gamma, I'm going to just do the appropriate location. When you use the face mill cycle, you don't have the peripheral C option, because the nature of a facing operation is it's flat. It's not wrapped around a radius the way a pocket could be. So pocket, you're going to see either the sheath Y, which is in the Y-axis of the machine, or the peripheral C. But when you get mill, you only get sheath Y. So you won't even see or have the ability of doing a face mill operation on the peripheral if you have a machine that doesn't have a Y-axis. I have yet to see a B-axis lathe that didn't have a Y-axis. These are really the baddies, right, of all the machines. So they're going to have all the functionality. And we're going to chain, or we're going to create two face mill cycles, and they're just going to be 90 degrees apart. First one starting at an index of 90, because I want it clocked 90 degrees off that slot, and the slot was at 0. Then the next one, when I look at it, it's going to just be a mirror image of the other one, and it's going to be 180 out. And what I also want to do is I want to make sure that I gate my facing cycle so I don't overcut here. So I'm going to use a basic position and then tell it to limit the overall. Okay. Back into our program, I'm going to insert below open slot. So I just want to make sure my highlight's sitting on open slot. We're going to go to milling, face milling. You don't have to keep telling the tool. That's redundant. But if I start to move things around, it's kind of nice to have the tool in there, because I don't have to remember what was modally loaded. So it's kind of up to you. And speeds all the same. Position of it. So remember I said you don't see the peripheral C here. The nature of a facing cycle, it's got to be flat, and that can't be flat. That's wrapped around a radius. But in the Y or face in the B, so here, but all the facing cycles require a Y-axis to be there. May limit right? So my X is going to be going up and down. Z is back and forth, so that's in a Z direction. The Y is across the part. Where I want my first position to be, probably 90 degrees. 90 degrees. Back edge, according to my print, if I look at it, this back edge is 50 millimeters back. So I'm saying, hey, I'm going to start 50 millimeters back. I'm leaving a little bit on my Y. So we'll say 50 mil on one side. X is going to be my location, but this isn't diametric. This is radial when you get to milling cycles. Got a diameter of 40 mil. Then the finished surface is actually at 20. The rough surface, because it's cylindrical, is actually out at 25. So start at 25, and then end at 20. How far over do I want to go in my Y-axis? 100 mil should be fine. That's why I'm giving it 50 mil on either side. I don't need another 50 mil off of the Z0, which is the face. So I can just come back 50 mil from my negative. That's going to do a feature. Starts at this back edge and comes out. And then I am limiting my depth by this field. Stepper cut. We'll just take it all at once. One shot. We can right back to the facing cycle. Actually, I'm just going to copy mine and paste it in and open it up. And then I can give it just the 270. And as long as I made all my numbers right on the first one, I should get 2 flats. Okay. There our slot. Now we're going to index 90 degrees. And you're going to start milling across. To surface, it's going to try to always start at the furthest point away, hence why it's starting out in the Z positive, even though I gave it the dimensions working backwards. Doesn't really matter. 6.5 doesn't the other. And 2 flats. And we get our 2 flats, 180 degrees opposed, and 90 degrees off of the slot. Some kind of get confused where C0 is, so I even find myself just, let's get some geometry in and kind of get my head around where this whole thing's falling. And then if I have to, I can index things 90 degrees from each other. Again, she would continue on with the transfer and the machining of the back up. So that's some there. Now I actually drill some holes. I'm going to use the drilling cycles, the live tool drilling cycles that are in the control. We link events just like you would in the lower technology machines. The big here is paying attention to the strategy I'm choosing. So is it face, is it peripheral, is it sheath, and making sure I carry the same strategy through from my can cycle to my position locations. And mix these up. These things won't chain anymore. And the position patterns always have to chain. So make sure that we remember to do that. So to Sinu train, I'm going to continue on with this example. Let me bring up our part print so we can do that. So as we're doing 4 drilled holes, see drilling 2 per surface. So yes, I'm sure it's hard for you guys to see. These are hidden lines or hidden holes. So the exact same 2 hole locations, and the nature of us flipping the over, it's the next positions. It looked from the top view with the hidden view that you have 4 holes. We actually only have 2, so that's what we're going to be plugging into. We're going to be this top hole and that lower left hole. Do them again on the opposing surface. So below face milling, I want to set up a drilling cycle. I'm just going to do a standard drill beam. Certainly this could be a peck drilling or one of the other many cycles we have. According to the print, I'm doing a 6 millimeter hole, 10 millimeters deep. So I'm choosing a drill, 6 millimeter drill. Again, it's commissioned or created, pointing E, The system's automatically going to flip that BS down 90 degrees for me to drill the holes. I'm not too worried about it. In this case, you're going to put something a little accurate when you curve the part. Now, do I want to position with the y-axis, or do I want to position with the C? So in my case, I have holes that are off-center, right? They're offset to the center line, so I have to position in Y. And just remember this option, because it's important to reflect this when we the position screen. Couple standard options, and I accept. We get the normal open bracket, so it means we got to link it to something. I got to link it to my positions. Use some random holes. And there, I mentioned you have to choose some strategy. You notice if I choose the strategy, they don't link together. So it's important to use the same strategy and just carry it through. So what position am I starting to drill from? We said before that bottom flat surface was at 20 millimeters radially, so that's why I'm using a X020. It's the rotation position of the first set of holes, 90 degrees. Rotation, that'd be this top hole, so I'm 7 millimeters off in the Y, essentially right here, 15 millimeters back in the Z. Next is 7 millimeters in the positive, and I'm back 30 millimeters. So those two holes, I hit accept. Now, because I have the appropriate strategy, I do a random set of holes. 270. I have all 4 holes. System automatically driving that tool down to a B-axis 90 position and drilling my 4 holes. So let's take a look at that. Here comes our starts before we can drill holes on the flats. Swings the B down. I even see the B here showing the 90 degrees. And then sitting at my clearance position, waiting for me to come up with another operation. All right. So that's start to handle some peripheral drilling. Base drilling as well. In fact, in our example, I want to put a 16 millimeter hole straight through this part. Now, in case, to make it a little bit more interesting, I'm going to say that the drill that I'm using cannot drill all the way through this 150 millimeter part. It's a 60 millimeter hole, so that's not a uncommon scenario. So I'm going to drill, and I specifically chose to do this right transfer. So I want to drill from one side, a little over halfway through. Then we're going to transfer the part, and we're going to, same tool, flip that spindle 180 degrees, finish on the back side, and we'll get our through hole. Now, just to keep things a little bit more interesting, I decided to use the solid drill functions. You're going to get a chance to see how solid drill is created. I'm going to use a centric drilling cycle because in this case I want to actually hold the drill stationary and in the main spindle or the sub spindle. You don't always have to use live tools, right? I still use centric scenarios. It's kind of six doesn't the other. Really doesn't make any difference either way, but the tools are still there. So let's take at that. So back here after my positions, I'm going to want to go to drilling. To my centric, which is my first option up, right? The rest of these cycles down below, these are all live tool cycles, right? So it's going to run the milling spindle. The centric is going to run the main spindle holding the tool rigid in the location. The tool is going to be a solid drill. Now the solid drill, when building a solid drill, let me just get to a new, you're not seeing it in the favorites. So if you're looking for something you don't find in the favorites, go and drill down into the different cutter options. Under I see solid drill. So between a solid drill and a twist drill. So solid drill you can still run live, being really referred to as what we like to call an insert style drill. And the biggest thing is the solid drill. The solid drill doesn't force you to put an angle value in because it's got a flat bottom. So I have a tool that's flat bottom drill. I like to use the solid drill. It just keeps me from having to plug numbers to kind of make a flat bottom, right? Standard drill. So enter projection from the spindle face out to the tool tip. It's centric. So in the centric cycle, it can only ever allow this to drill at a B0 or B180 location. So we don't have the ability of flipping to a peripheral surface or anything because centric, the nature of centric, it's spinning the spindle. The tool is being held stationary. So fill out the rest cycle as normal. How deep am I going? If I want to use peck, what would my max peck? I'm taking it all in one shot. I'm going to program stop because I don't need it anymore. Transfer, and I'm going to simply copy the center drilling. I'm not going to do anything different. The work coordinate's going to handle where it's going to drive this tool to do it. So look at it now. We're going to get a hole on both the faces. Come back. Now, a quick trick, I can do Control M to speed up my simulation and then speed it back down by hitting Control again. So now I can just get my partial drilled hole, do my transfer, and then red drilled hole, and then she's going to come down and she's going to turning the part. Look at this, cut view, and we can run it. So you guys a little different perspective. So we're turning it, pick up the speed a little bit with Control M, drilling our peripherals. Now the tool is going to come in. So there's our partial drill just past. We do our transfer over, and now there will be our blend. So getting there, we're just about done. We're at this side of things. So now we got some interesting stuff. We're going to get a chance to see how do I handle inclined planes. That's really where I want to get to, right? Because I got a B-axis lathe, so I want to use features that are going to allow you to take advantage of the B-axis lathe. At our slides, to inclined planes, I need to start to understand a little bit what we mean by the swivel cycle or cycle 800. Or cycle 800 does two key features or functions for me. It allows me to create an inclined plane and then set my tool normal orientation to that plane. Allows me to drive the orientation of the tool, but it's not going to move the work coordinate system. And that's the difference between the left option, the left feed you see on the side, or the right side. What happens to the work coordinate system? Work coordinate staying fixed, and it's just changing the orientation and managing the orientation of the tool. That being with the beta and the gamma. Excuse me, that should have been on silent. What's happening with the beta and the gamma fields, right? That's really doing that orientation of tool option. I want to create a plane and then have my Z plane be normal to that surface, or Z orientation be perpendicular to the plane, and then the tool automatically aligned to that plane. I'm going to use the orientation of the machine, and that's what we call our swivel cycle. Cycle allows me to do a couple things. It allows me to move the zero around linearly. It allows me to rotate the zero, and it allows me to move the zero around again on this new rotated plane. And at the end, when it's all said and done, it's going to be sitting perpendicular to that surface. And my Z is now going to be coming straight up from the surface. The Z is no longer going to be the face of the part. What we call swiveling with the swivel cycle instead of orientating the tool. For example, we want to create a plane. So we use the swivel cycle feature center and move my zero around a little bit too. So when I look at this, maybe those of us that have seen or used the Cycle 800 on a more of a milling type of configuration variation, the similar fields, actually there's a couple things that get pulled out of here that have over on the mill side, but pretty much it's almost identical. Tool change, I can retract strategy. Here, this is unique. I can clock or orientate the C position. You would obviously have that in a milling machine, but I would have it on a turn mill. That's where I can kind of spin my around, just like you've been seeing in the other cycles, where how do I position my C for that feature. Shift, the X, 0, Y, 0, Z, 0. That's linear staging of the work coordinate system. So that's doing that normal to the original coordinate system of the part. Swivel mode and swivel method is going to allow me to start to rotate things around. Now I can rotate or create a plane, created the plane, or rotated, and then shift my zero along that plane. So in case we're going to drill a hole in the center of the plane that we make. All right, if we looked at our print again, we have two 40-degree surfaces, we drill a couple holes in them. So shift things around once I'm all done. What's happening? Well, I can picture a work coordinate system, and here you have a little coordinate cube displayed. I knew before I start the swivel cycle, right, my X and Z is front center of my part. It normally would be on any lathe, Y center as well. First shift of 10 millimeters in X is really just going to slide the zero up to that corner that I want to pivot on. Corner of my plane. And I know that because I have a known dimension on my print. It's important you would have that value on your print. Now I want to rotate the coordinate system. In my case, slightly around the y-axis. And I'm rotating in a plus direction. I have a plus value in the y field of 45 degrees. The result of that is now your coordinate system is sitting still on that corner of the surface, but now Z is normal to or perpendicular to this new inclined plane. But not least, and I don't have to do this, but sometimes it makes it easier later, I'm going to stage the zero by sliding the work coordinate system up this new created plane. So we're going to move up the x-axis in a positive direction, millimeters. And then if I was to tell a tool, go 0, 0, 0 for x, y, z, it should be touching the center point of that plane. That my new zero is at the time of this swivel function. From there, once I swiveled in place, I can use the facing cycle, and we're now going to get to use the face B function. So face B is referring to the B axis, and if you want to do anything in an inclined plane with a swivel cycle active, you use face B, because face Y or sheath Y is going to then negate this plane you just created and go back to standard orientation of the work coordinate system. So selecting face B, we're selecting this tool path to the plane that was just created. So I do have to have created a plane prior to this. So your operations, like you see here, you're going to have a swivel plane, and then once you've created the plane, tell how you're cutting this. And this would be the same thing in G code. You'll have a cycle 800, which is a swivel plane. You'll have a bunch of operations, and that could be just G0s, 1s, and 2s, whatever it takes to do that feature. But that's an active to the core swivel plane. So we're going to do this for one side, and then we have to kind of flip it over and do the next side. But so let's get one surface created. Highlight below stock removal, because certainly I would want to have turned the feature down prior to putting these two flats. And here you can see this is where I have some known values, right? In the view A field. I know that the edge of my plane is 20 millimeters diametrically in a kind of a more of a milling type of scenario. So this becomes a radial value. That's my shift to 10 mil up. I get 45 degrees about y-axis. That's why we have a positive 45 in our y. And then if you look, I know the center line of the hole I'm going to put in later is 10 millimeters off of that edge. So that's how to slide my 10 millimeters up in my x-axis. No plane exists. It's found under the various cycles, and you have a button called swivel plane. Now, the swivel plane, like I was mentioned, there's two strategies, right? You have the swivel plane for planes, or you have the orientate tool. You do have orientate tool on as well here. We were allowing it to all happen using data in the gamma fields in the cycle, let's say. But I need to change the location of my tool and then come down and do something without moving my coordinate system. You can use the orientate mill tool. And in code, 700 has that same variation. So you can do an orientate mill tool with cycle 100 as well in the G-code side, or swivel plane. We're using swivel plane. Now, here, I'm probably going to want to grab the tool that I'm going to be using. So we're going to be using a 12 millimeter tool to mill this surface. So I'll let it do a tool change now. We can track plane wherever I want to back up to when I'm done by orientating my C. I may not know this, so in your first surface and see if everything seems to be aligned the way I want it. If not, you can clock it. So it's sliding my X up 10. Wasn't changing. My Z wasn't changing. So that was putting me right at this corner, right at the pivot point. A positive 45-degree rotation. And I'll shift in my X 10 millimeters up to the center. Things you want to get your head around once you start programming this method is where's the coordinate system when you're all said and done. And get your hands on a little coordinate cube. They're very, very helpful. At the end of the day, we saw in our previous slide, the system is going to be sitting right here. So up, Y is across the part. X plus is going kind of back towards the chuck. And that's important once we start putting our physical cycle, in this case a milling face mill cycle, to kind of think about where the geometry is. So millimeter tool, some speeds. I need to make sure I choose face B. I'm not worried about gating anything as far as my cutter path. Everything is kind of open around it, so I leave that. We're going to choose our amount of facing. So the center of this feature is 0, 0. So here, how much in my X, I really know, well, I know that 10 millimeter gets me from the center of the bolt hole pattern, which probably is the center of the feature, out. So I need at least 20 mil, and there's 0. So if I did maybe minus 15, and later down here, I did 30, let's say, off of that back edge. So that's going to be back here. Remember, plus is up. All right. So minus 15 somewhere there. I'm going 30. That should be okay. My Y, we'll go 25. And we'll go 50 mil for the Y. My Z 0 in this case is something a little bit above. I don't really know, so I can guess. Maybe I'll give it 5 mil, see what that does. And I'm ending at a 0. So the plane I created, that's establishing Z0 to be this surface. So I have some plus stock. How much I have, I can mathematically calculate it. I'm not that worried. I'm going to get some plus stock. I might, if it looks taking too heavy a cut, I give it a little more stock. In my case, I'm taking this all in one shot. Simulate. And we'll keep a little faster here. All right, so is our just transferred. I just drilled. Okay, so now we're on the back side. We're turning to get our swiveling tool. All one cut. Obviously, you would probably do this in a couple passes. Here I see the feature, just like I see on my print, is off 90 degrees from these flats. So I wanted it. So my C0 was a good strategy. Now we've got to get to the back side. The back side, I want to really just mimic that exact thing, but spin the core system 180 degrees out. We can use, we're going to have to create a new plane, right? It's a swivel plane, and just going to have a repeat of the same cycle. And that's what's going to spin it 180 degrees out for me. So I don't have to try to shift anything into the bottom. I can just pre-stage the part so sitting in a plus feature. Then I'm going to get my two flats. Oops. All right. Oops. Now, of course. All right. Give me 1 second here. All right. Let me transition back. My computer had a little Farfignugan in there. All right. So I'm going to continue with my milling of my inclined plane. So I really need these two events. So to just highlight them, copy them, and paste them. I'm going to go back into the swivel plane, and I'm going to tell it to index the swivel plane 180 degrees. And this face mill feature can stay the same. I don't need to change anything. And then we simulate. We should get both surfaces. Kick the speed a little bit. Transfer. There's our backup. Okay. We'll let it finish up here. All right. Position handled with that orientation of the C in the swivel cycle. And we can jump to each two surfaces. We don't mind. We just got a couple holes to put on the system or on this part, and then we're going to be done. It's going to be drilling and drilling in an inclined plane. Now, I intentionally kept this pretty easy. Certainly, there could be a whole bunch of holes in these surfaces, but the key here is we're drilling on this surface. So anywhere on that surface that's created. So we're going to choose the drilling cycle, and now we're going to use the face B strategy. Whenever I want to do anything, milling, drilling on an inclined plane, where I'm using the B axis at a position other than 0 or 180, I use the B option. But with that, I need to have created a swivel plane. So we're going to come in, we're going to choose our face B option once I've given it a swivel plane, and it will use the act swivel plane. Careful, if I'm driving tool change, plane may or may not have been maintained. It's really up to the OEM when they go through their tool change macro if they want to cancel the plane or keep it active. So if you know, I would defer to the alternate, which is I'd rather be redundant with my planes and safety perspective, because I know I just sent it through a tool change. So I'll actually add a plane in ours. Come in, we're going to drill a hole. We're going to choose our location. We'll do next hole, and here I'm just going to show you a quick little way of doing some repeat commands when I have some repetitious functionality. It's having a whole bunch of copy and paste. So on mill, I need to do a new plane. So I'm going to go back to my swivel plane. Now, I keep it at 180 because that's already staged. That was the last one I was working on. And then jump back to 0. That's okay. I want to make sure I have the plane, a drilling strategy. Now, my part, if I get my call out for my 8mm hole, I do want to probably in this plane. Yeah, I'm sorry. I do want to call out my 8mm drill created pointing towards B0. Tract, orientation, location. So all this stuff stays the same. All right. I don't have to do anything else because this is now establishing a 0 at the center of this hole that I want to drill. From there, we're going to use our cycle. Do a basic cycle, 8mm. I know my depth is in my call out, which it looks like it's 2mm deep here. And make sure this B. That's important, right? And then I go to my position locations. I can do some random locations. I'm going to choose face B. Z0, Z is perpendicular to the surface. So 0 is going to be the top of this plane, which is where I'm going to drill from. And my location for my drilling is 0, 0. Of dimensions, so I can zero them out. It's going to drill one hole right on the surface. Now, when we start to get to some of those repetitious events, sometimes it's nice to not have to keep copying and pasting and maintaining the same geometry in multiple lengths. That's an area where I like to use the repeat command. Now, the repeat command, you can use all kinds of different markers to tell it where to go to. Probably the easiest things to do is to go in and your edit function, go to numbering option, and give yourself some n numbers. Plug in some n numbers, I have some automatic point locations. So what do I need to do? Well, I need to do a new swivel plane back to 0. So we're going to do a swivel plane, 0. I really need to just redo the N180 and 190. And let me just do a, oops, I'm going to remember, get a number on that one too, so they're all the same. So if I do a quick little G-code line, word repeat, space, and what n numbers I want to repeat between. If you want to just do one, you'd have to just duplicate the number twice. In my case, I want to go N180 to N190. Well, we should get both sides. The way with sequence numbers that's real handy is if you want to use go-tos. Like I had to go-to in the beginning of this program and jump really over all this first op stuff and allow me to just pick up at the back. But here, let's just run it across, speed it a little bit so that we're doing our turning. There's inclined mill plane, right? The first plane. Drilled at 180. I didn't spin again. It should just come right down. Drill my hole. There's hole. There's my next drilled hole. And if I did my job properly in my position and my depth, we should break through. Get a nice little breakthrough. So I'm going to do a cut view. And let's cut it right there. There we see. A crawl came through, broke through. It did not. This is just the breakthrough there, so it looks like my numbers were good. All right. So job done. I can activate the cut for now. Final operation, looking at the print, is I have some holes, but kind of like a bolt tool routine on the inclined plane. So it's different. So if I was to use a standard bolt hole on this surface, it would be working around the surface, but we do have an option to kind of rotate around. So I can create a plane and rotate it around. There. Oops, sorry. I want to do our point. That one. From here, just slowing down a little bit. A chance to catch up. A little slow today. All right, sorry about that. Now we got a mouse back. Okay. Interesting. Technical difficulty. So we're going to swivel cycle a drilling operation. We use a face B, but we're not going to drill just on the plane we create. We're actually going to use a C-axis rotation option. Here, I use face B drilling strategy with a face B selection in my bolt hole routine. But I see then basically transfer that all the way around this bolt hole pattern. So this is a feature we add. So in Sinumerik, we're going to create a final plane. And what's going to happen is this plane is actually going to be back on this surface. So I got to do a little bit more motion here. This is where I'm going to actually create my new 0. It's going to surface. So swivel plane. I'm going to, I can leave that in, that's fine. I retract. Now I'm not bringing my X up 10, this corner. I'm bringing it all the way up to the surface, which is 25 mil out, right? Give it a positive 25. Shift back is going back to this corner, so I'm sliding my 0 back. 0 pointed straight out from the surface. 40 mil, that's a negative 40 mil in Z. Right? She comes back to do a rotation of 45 degrees positive. Puts X, Z coordinates right here, so X is moving back to the surface. Z is now partly out off the surface, walk across the part. And I want to do a final shift to the center of my bolt hole for my print of positive 7 mil in X. That's going to plug that X, Y, Z coordinate system right there on the whole location. From there, we can start our feature. In location, I'm going to drill. I'm just going to do a basic drill ream. I'm going to still be using a face B because I have an inclined plane. At my depth's a little deeper now. It's 45 mil per the print. What is going on here? Awfully slow. Sorry about that, guys. I'm not sure what's going on. My feed is an issue. Okay, I have my drilling enabled. I'm going to go to my position screen. I'm going to do a bolt hole pattern. And I still use a face B strategy. I'm going to use a with C axis as opposed to on plane. I use on plane, that's going to give me a flat bolt hole pattern, keeping the C stationary. That C, now it's going to position around. Just plug in, where am I starting, where's my Z datum, it's in this case, where's my X, Y, 0 is going to be the center of my bolt hole, angle of my first location, and then how many do I want to do. Right, we should now have a fish part. So we'll let it simulate the whole thing, just give you a refresher of all the ops. Do first peripheral face, it's actually a face Y or sheath Y, right? Or peripheral milling, but we want to use an X and Y motion. And we face off the next segment. I'm going to increase our speed a little bit, we'll go to 100%. Drill our holes. Back turn. First surface, second surface. Drill. Your bolt pattern wrapped around. Recap. Really, the biggest thing from a technology side to kind of get your head around is where the orientation of B in the spindle. Then from it, so we're going to use our beta and our gamma fields to rotate things around. I'll methodize everything as if it's on the main spindle. Mirrored work coordinate, I'll handle that. I want to get to my inclined planes. I need a cycle. Swivel cycle, any cycles I want to use, I have to do a face B option to allow that to work on this new inclined plane. Well, I'm going to find this is going to drive very, very similar to a standard lathe. That concludes our topic for today. I thank everybody for taking the time out to watch this seminar, and I hope to see you again real soon.